The study guide has just been sent to Canvas. It's 8 chapters plus whatever we discussed today. I'm recording the class. It's just theoretical discussions about optics, the last chapter. Let's show you the slides, and then I will upload them so you can read them during the weekend. And then Monday, what time will be best? Because the school is still in session, but we normally are done by 3 to 30. So I can probably offer you guys office hours on Monday between 3:30, and 5. So 1 hour and a half. So you can come in and ask questions, but the exam is from 3:30 till 6 on the Tuesday. So it should be fine. The study guide has a list of topics. I would suggest you guys go over the quizzes that you had and the tests. That will be, and if you need, you can go through any of the recordings or the lecture slides, but it should be fine. There are always going to be some misconceptions. It's okay. We've been doing this online, and I know that it's not probably the best way to do this, but we have tried, and I believe that we've been successful, at least for the learning outcomes. But let's go into the last chapter. So we talked about electromagnetic waves. And optics. Right? Oh, sorry, electromagnetic waves. I just need to focus on where the presentation is now. How do I make this presentation? Slideshow. Wait a second. There it is. That's why. Okay. So when we talk about electromagnetic waves, we said that an electromagnetic wave has an electric field and a magnetic field component, and they propagate at the speed of light in vacuum. But the best example of an electromagnetic wave will be light, as you are seeing it there in the picture. Right? The light from the sun is not really yellow, it's white. We see yellow due to the atmosphere, and the sky is not really blue. It looks blue because of the scattering of that light in the atmosphere, the white light. So, what's the scattering, right? When light hits the atmosphere, there is something we call, and we're going to learn, refraction, which is the idea of light changing its direction because it goes from vacuum to a more dense environment, in this case air. And the atmosphere has different layers. Now, light scatters because light is made of photons. Those are small packets, what we call the bundle of light. But light is also a wave. So you see what you are seeing right now in the picture, you see sort of like a diffraction pattern there. It's light can diffract. And I remember when we talk about mechanical waves, when we talk about the Doppler effect and all that, I said that there is a double slit experiment that we're going to talk about today, where light behaves like a wave, like water waves, going through slits and interfere with each other. Right? So, the rainbow, if you think about it, look closely at here. Let's see if I can magnify it. There. Red, yellow, and there's a bluish part here. So that happens because light is refracted and diffracted. When there is a rainy day and there is sun, that normally happens in the spring, right? Also in summer, by the way, but mostly in spring, you will see rainbows because light from the sun is being refracted and diffracted in the water particles, water drops. And that's the spectrum of light, the visible spectrum that we talked in the past chapter, right? Now, obviously, we need to remember the units. By the way, units, very important. That's going to be in the exam, okay? Conversion of units. But the range goes from 750 to 400. Violet. Yeah, purple, right? So it's not really blue. The extreme is purple. Although violet or / purple, it's probably very dim. So normally the one that we focus the most is the blue part. That's why, for example, here you have, right? Now, since light is a wave, thanks to Huygens and other scientists more than 300 years ago, we know that there are, just like water and with water fronts, and when we discussed that in mechanical waves, and remember when we discussed about a stone or an object falling on a pond of water, and you see water waves forming, light is the same. You can have a light source and you see waveforms. So to study light, at least at the beginning, we can use the perpendicular lines to each wavefront, which is shown in B there. We call that rays. So we can use ray optics. Ray optics is used to study reflection, refraction, and to determine direction. Now, the speed of light is 328 meters per second in vacuum, and the wavelengths of light are very short, in the order of nanometers, right? Reflection. If you have a mirror, and you have a light source, a laser pointer maybe, and the mirror is flat and shiny and polished, you will have your reflection there, where the angle of incidence is equal to the angle of reflection. And then you have a normal line. Okay? That's called specular reflection. Right? You can normally have that in a mirror or in the surface of a calm pool or lake. Okay? All right. Yeah. That's the law of reflection, by the way, that the angle of incidence is equal to the angle of reflection. Now, that normal line is imaginary and is identical to the idea of the normal force that we discussed in chapter 2, I believe. Chapter 3? Chapter 2. Oh, I forgot to add chapter 3 in the study guide. Guys, in the study guide, conservation of energy and work, I'm going to have to update that. I forgot to put that in there. Because chapter 1 is motion, chapter 2 was these forces, and chapter 3 was work and energy, right? And power. So I will update it later. But anyway, the normal is perpendicular to the surface. That's what we call it normal. And we use that to measure the angle of incidence and reflection. So that's the law of reflection. But is this always the case? No. Right? You can have reflection on the ground, on the floor, on the pavement. Like that. Diffuse reflection. Okay? It's for a non-smooth surfaces. So the law of reflection still applies, but the rays will encounter segments of irregular surface oriented at different angles. So you will have them living in different directions. So you still have the law of reflection, but it's more like random directions, right? You have different V's. See what I mean? Here. There, but then you have this one. Right? That's why. Things that you observe have color because light penetrates into the material and is partially reflected. and partially absorbed. Guys, I just talked to you guys about the greenhouse effect when I say that. Color is good, yes. The reflected light that leaves the surface will have color. But, well, let's not talk about the greenhouse effect. Let's talk about the Rayleigh scattering. Rayleigh scattering is the reason why the sky is blue. It's because light is refracted in the atmosphere, and the blue component is scattered. It's reflected more efficiently, and that's why you see blue there. During sunset, all the blue is gone, and you have the leftover red. That's why sunset is orange, reddish. Okay? So, that's good when you want to study light as a ray. And we can use this concept for refraction as well. And for mirrors and lenses. But we know light is a wave. How do we know that? By this. If you have a narrow slit and a light source, normally monochromatic or coherent light, like a laser pointer. If you place a screen like it's shown in the picture, you will have what we know as a diffraction pattern. Alright? So light doesn't spread out after passing through a window nearly as much as sound does, but diffraction can be observed through very narrow slits. That has to do with the wavelength. The wavelength of visible light is very small in comparison with the wavelengths of sound. Right? Regardless, the fact that light can be diffracted was a key for scientists to understand or to realize that, well, light has a wave-type behavior. What you're seeing that there is the Young double-slit experiment, guys. Thomas Young used interference to prove that light is indeed a wave. If you pass light through two narrow slits that are separated, that are very close, so a separation between the slits can be in the order of the millimeters. Millimeters, not microns, millimeters, right? You will see the interference pattern as shown in the picture there. There are equations for that, by the way. The equation depends on the separation between the slits, the wavelength of light, and depending on which fringe you want to observe, you have what we know as the order. The equation looks like that, by the way. Alright. So the distance between two adjacent bright or dark areas is determined by the distance between the slits, the distance between the screen, that's true as well, and the slits. And also the wavelength of light. Now, it's just trigonometry. If you ruler here. No, it's fine. If you want to see here, there's an angle here. The distance between the slit is this. So you have like a triangle here. So obviously in a triangle, you want to solve for that. You need this distance. I need the angle. But guess what? The angle depends on the wavelength, depends on the distance between the slits. I'm going to call it small d. So once you have this, and then this, you can find this here. We normally call it y. In the slides, they call it s. If you're interested to know the equation for the interference pattern or the interference, is given by d sine theta equals to m lambda, where m is the order. For example, the one here, we call it the central maxima, this one here. So here m is equal to 0. If m is equal to 0, that means theta is 0. This is 1 and this is 2. So that's just basically how it is. There. You can also have interference with mechanical waves, all right? And you can have interference that we use interference in astronomy. Radio telescopes. Let me show you very quickly. Oh, it's gone. We call it interferometry. In New Mexico. So you see these antennas. So each one of them is observing a point in space. They all join together and they all go into a correlator. The correlator joins the signals of all of these together. This is the VLA in New Mexico, by the way. That technique is being proven to be more effective than having just a very large disk like the Arecibo, which by the way doesn't exist anymore. The other thing that we know from electromagnetic waves, guys, is polarization. All right, polarization is the idea of light changing its direction because of going through it could be in some cases an analyzer, it could be in some cases a polarizer. And you have heard about polarization, guys. Polarization is the idea of changing or revealing the transverse nature of light. Polaroid filters, guys, are like lenses, and we use them in sunglasses, so they absorb light passing through unless light is polarized in certain direction. For example, this better example, right? You have different directions incoming, and the polarizer focus in just one of them, the vertical direction. Polarization is also the idea of, in your cars you can install polarized glass, so nobody can see, but you can see from in to outside, but nobody from the outside can see what's happening inside. That's the idea also here. There it is, right? So you cannot see the face of the woman, but the scientist or that person there can see us. All right? Or here. Right? So polarization is just absorbing part of the light passing through. Light polarized in a given direction passes through the Polaroid and is largely unaffected, the light that goes through. We are going to assume that this always happens at 100% efficiency. It's not 100%. You can tell here it's not really 100% or here, right? It's not really 100%. There's always some room of error, but that is basically the idea of polarization. All right? It's just having a wave, an electromagnetic wave, going through a polarizer or another. Of course, the intensity of the wave will change, but we're not going to worry about that for now or in this chapter, in this course. But the intensity changes depending on the angle of the polarizer. It's a very nice experiment that we can do. Okay, so polarization, interference, and diffraction, they give you clues that light is a wave. Right? Now, for reflection, I said that we use light as a ray. Because regardless, or even though light is a wave, we can use the wavefronts to draw those rays. And they are very important because we can use the idea of light behaving as a ray to do this. If you ever wonder how you can see yourself on a mirror, now you know. Thanks to the law of reflection. Your feet here goes to this position and your eye, basically, right? Goes towards your eye. To see the image of your feet due to the reflection here, happening here, you will extend the reflected ray towards the mirror. Here is what we call the virtual image. It's virtual because it's an image that you cannot really touch. It's an image that is just there and is formed behind the mirror. For your eyes, you can also have your middle part there and then extended, and then your eyes and your face there, and then reflected there. And also this will go towards the eyes. A property of plane mirrors is that the distance between the object, in this case the person, and the mirror is the same as the distance between the image and the mirror. That's only for plane mirrors. Yes, most of the mirrors that we use in daily life are plane mirrors. They are flat, smooth. So they are perfect reflectors. So some of the rays leaving the mirror are going in the proper direction to enter our eyes and give us an image of ourselves. So yes, the image appears to be on the other side of the mirror. The dashed lines that you see there, guys, they show you the apparent path taken by the rays when you trace them back to the image. So this line, and this line. Now, just as you probably expect, in science, plane mirrors are just okay. We can use them to re-reflect light or reflect light. For example, in a camera. Right? That's an old camera, right? You have a camera lens, and then you have a flip mirror there, and you have the film. So back in the day, actually there are cameras like that nowadays, but they use pixels, and they use like Photoshop. They use chips and pixels, and it's different nowadays. It's not really a film. But that's how it used to work. Okay, we'll talk about lenses in a bit. Now you're probably wondering about the one-way mirror. A one-way mirror is made by partially coating the glass, right? You've probably seen this in movies. So it's like a half silvered mirror. So a person, you can see a person on the other side, but that person cannot see you. It's a one-way mirror. It will appear to be an ordinary mirror to anybody in the room. That's because in the bright room, light is reflected off the half. So clearly, you see reflection happening in just one side, in the bright side of the room. In the dark side, you don't. You only see the image forming. Alright? So, light cannot be reflected because it's totally coated. Alright? An example, I've never seen this, but when I saw this slide, I'm like, is this what they're going to be using now in the schools? Hopefully not. You see what I mean? Like the teacher will be, the kids will be in the other side, and teachers will be, I guess would be a good way to restart at some point, but I mean, I can see it being done in college with adolescents, but not with kids. Anyway, so one person, actually, you could use this to observe a class, right? So the teacher is with the student there and the other person is there. So the student doesn't see the teacher on the other side, but the teacher can see them, right? So there you are. Okay, so mirrors that are either like this or plain mirrors are good, and there's a usage there for plain mirrors, right? But in science, guys, we like to magnify or diminish the size of an object, depending on what we're using it for, right? When we talk about lenses, you will see what I mean. Look at this. What you're seeing there right now is a curved mirror. It's a concave mirror. A concave mirror is a mirror where the light is focused towards a focal point. And the interesting part about this is that you can have a magnified image from a concave mirror. Can somebody tell me which doctor, not doctor, but what profession uses concave mirrors? In what situation would you think a concave mirror would be useful? I mean, it has to do with medicine, by the way. When you guys go to the dentist, let me show you. You probably know this, right? This, guys, is a concave mirror. The dentist uses it to magnify your tooth and perform, no operations, but the treatment, cleaning, or anything, or extractions at some point. So there you are. However, just as we have concave, we also have convex. A convex mirror is used to make an image virtual and smaller. Well, both of these images are virtual because they are on the other side of the mirror. But this one in particular is virtual and smaller than the object. When do we use convex mirrors? We use them a lot, especially in outdoors. You've probably seen those mirrors in some intersections. I've seen them in New Jersey. When you have an intersection or a driveway in the middle of the road, or in some places, in some national parks. I don't know about you, but I go hiking a lot. When I go to Delaware Gap, and you are going into those parks, sometimes the intersections are very narrow. So they use those, so people that are going to enter or leave, they can see what? Cars incoming. It doesn't matter if they look small, at least you see that they are coming. I've seen also these mirrors in gyms, in the lockers. They have them there. So they can actually see everybody that is coming and leaving. I don't know what's the reason, but they have them in there. So convex mirrors, they have usage, all right? Okay. Your rear side mirror in your car, guys. That's the best example. Your rear side mirror, the one that you use to see trucks on the other side coming, is a convex mirror. That's why it says in the mirror that objects seem to be closer than what they look, because of how they are diminished. So the convex mirror in your rear side in your car should be used just for orientation, right? Even though that if a car looks too close, guys, do not change lanes. Probably the car is just next to you on your blind spot. So there. Now, nice application, right? In science, we use mirrors in telescopes. What you're seeing there right now is a Cassegrain telescope model. You have a primary concave / parabolic mirror with a hole in there. And then you can have a secondary plane mirror here. So light bounces back and then goes to this secondary mirror and then goes through that focus. These telescopes are large and we use them to examine stars, galaxies. Reflector telescopes are used for stellar observations. Stars, galaxies, right? Maybe exoplanets, no exoplanets, no. Well, you could, but mostly objects that are very farther away from the solar system. Reflector telescopes, refractor telescopes, however, that we're going to talk later, they are used for objects that are not very far from us because they use lenses. There you go, right? There it is. Okay. But even though we have very large curved mirrors and very large telescopes, we always have issues with our observations, and that's mostly because of spherical aberration and chromatic aberration. Besides the atmosphere itself that is very blurry. So light incoming gets absorbed or gets, because the medium is very turbulent. So our best telescopes, for example, images that are very clear from the, galaxies or galaxy clusters, normally are taken with the Hubble Space Telescope, because the Hubble is orbiting the Earth. As the Hubble orbits the Earth, right, it avoids the atmosphere. Okay, so just as an extra, you can see the difference between one image and the other. One of the main reasons to have this difference, actually, sorry guys, this is an image from the Hubble. What happened there? When the Hubble was launched in the 1990s, in 1990 actually, the image that you see on the left, that was the image that we were getting. So it was a complete disaster. That is because there was a spherical aberration. All right. So what we had to do is that astronauts that were sent using a space shuttle were there to install corrective optics on the instrument. And then they were allowed to do the proper observations as you see in picture on the right. That was going to be a major disaster, huh? All right. How can we use telescopes on Earth to do proper observations using our curved mirrors? Easy, not easy, but now it sounds easy. First of all, we use CCDs for cameras, so we don't use films. So a CCD can process thousands of or tens of thousands of pixels, right? And it works by signals that goes through the pixels, and then you have a charge. That charge is in that's induced currents there, right? They can actually get the image with better quality, and you can get far more resolution and far more amount of pictures than we had back with the films back in the day. But the biggest issue with our telescopes here on Earth, based on the ground, based on Earth, is the atmosphere. Because as you know, light is being refracted in the atmosphere. So there is it gets very blurry. So is there a way to correct our instruments to make up for that? Yes. What you're seeing there right now is an example of that. In professional astronomy, in large observatories, like for example in Hawaii, Mount Kia, What they use a sort of like a laser pointer. They use a bright star in the field, or they recreate a bright star using this laser as a reference. And then they use what we call adaptive optics. So this technique, in some way or form, it reshapes the shape of the mirror. Look at the difference. Right? So what they do is they track the turbulence and they adjust the mirror 10 to 100 times per second via equators. And that's the... So obviously, to trace the turbulence, we need to use a background star or a artificial star. We do that every night because every night the atmosphere may be, in a particular situation, the density might be a bit different. Look at this difference, guys. Look at that. It's enormous difference. The details. Yeah. So it's possible for us to correct for the atmosphere and the turbulence. Alright. So that's a map there, guys. We just talk about mirrors, concave, convex, and plane. And the fact that with concave and convex, there are real-life applications. You can have virtual images, larger or smaller than the object. It depends on the type of mirror. All right. And just so we can go towards one of the last sections will be refraction, guys. Again, using ray optics, we can study refraction. And I already explained, it's basically the change in direction of the light. And you see it every day, for example, there. When you have an object in glass, in this case a pencil, it looks broken because of the refraction. Right? When you go to the pool, and the pool doesn't seem very deep, that's because of refraction. Now, refraction is not the only thing that happens. You can also have reflection. You have an incidence, and then you have reflection, and then you have refraction. Now, there is a way to relate both angles. We call that Snell's law, or the law of refraction that states that the light is bent toward the normal. If you're going from a medium with a lower index of refraction to a higher index of refraction. What is the index of refraction? The index of refraction, guys, is the factor, unitless, so no units, that allow us to measure the speed of light in different mediums. So yes, the speed of light is a constant in vacuum. And even here on Earth, the index of refraction is so tiny that it's almost the same as vacuum. The index of refraction of vacuum is 1. In air, it's around 1.000077. So it's very, very close to 1. So normally here in the atmosphere, in air, right, we can assume the speed of light to be almost at the same speed as in vacuum. Now you're probably wondering, so what happens with the refraction in the atmosphere? Well, the composition of the atmosphere is different because we have different layers. We have the exosphere, the mesosphere, the stratosphere, the troposphere. We live in the troposphere. But as we go farther and farther, the temperature and the pressure changes. So the density changes. In any case, light will do this if you're going from air to another medium with a higher, and every medium, glass, water, right, they all have indices of refraction that are higher than 1. 1.5, 1.33 for water, right? So there is always this idea of refraction happening there. All right? Yeah, so there you are, right? So on the left, you have a coin in an empty glass. On the right, you have the coin with the glass. Oh, there you are, right? That's the perfect example. So when the coin is immersed in water, you will see the coin closer to you. That's because of refraction. And we call that apparent depth. So this can be extrapolated to the sun. The position that you see of the sun out there is not a real position. Right? When light is refracted, we find the real location like that. So the coin, right, as you can see here, is here. Now it gets refracted, and we use a refracted light, we extend it, just like we did with a mirror, right? But now we're using the refracted ray, and then same here, and we find what? We find where the apparent position of the coin is. All right, guys. I think that is almost what I wanted to explain you guys. There is something called the index, the critical angle, which is, okay, actually the critical angle is very interesting. If you guys have ever done scuba diving, or being in water, submerged in water, immersed in water, there is an angle where your eyes cannot see the surface anymore, or beyond the surface. We call that a critical angle. When the light source is not in air, but is in water, there is a point, or there is an angle towards which your eyes won't be able to see past the surface. All right? That angle depends on the indices of refraction of the medium entering and the medium leaving the light. Okay. This is a good experiment, guys. Normally what we do in the lab is we use a piece of glass and we use a light source, and we can find and we can actually verify the angle in glass, angle in air, and we can find the index of refraction. You can see here, right? The angle in air is 60. The angle in... Is there a relationship? There is one. You don't have to worry about it. Just remember that because you are going from air to glass, the angle in glass has to be less than the angle in air. All right? And that's the concept of critical angle there. When light does this. If light leaves from one surface to the other, that means you can observe what is on the other surface. But if light is doing this or this, you won't. That's critical. That's total internal reflection. Where do we use that? Periscopes. Periscopes, we use this. Right? Anyway, guys, that's it for optics. Okay. The application for refraction, the main application is just lenses. Right? And the idea with lenses is just that light refracts and converges to the focal point, which is given by the glass itself. All right? We have two types of lenses, just like we have two types of mirrors. We have the convergent and we have the divergent. All right? Where do we apply lenses? In glasses. If you wear glasses, you know, to magnify an image, to bring it closer to you, an object. And we also use lenses in telescopes, refractor telescopes. The telescope that was invented by Galileo used a glass. And don't underestimate it, because he was able to observe the Galilean moons, he was able to observe Jupiter, Saturn, the rings, the phases of Venus, and the phases of the moon. Right? With that telescope. Don't worry about image formation, guys. I just want you guys to understand the difference between these lenses and how we can use them. Convergent lenses These are the ones that we use mostly in real life, okay? In telescopes, for example, we call them the objective and the eyepiece, or compound microscopes. All right? All right, guys. So what I want to show you now is the study guide. As I said, this should be, caramba, this should be 0, there you are. So, free will be energy and work, all right? What you need to focus here is the kinetic energy and potential energy. Hooke's law. Hooke's law and elastic potential energy. Conservation of energy. The work energy theorem. Work and power. So I'm not going to test on the whole chapter, but they are here the main topics you should focus. For sure you're going to have a question to convert units. A question on kinematics. It can be theoretical and one problem or exercise. You are going to have to do, yeah, you have enough time. I'm probably going to give you, maybe to calculate weight, given the mass. More than the law of inertia, I would say Newton's state. What do we call the first law? The law of inertia. So the concept of inertia. Problems using Newton's second law. Don't worry about friction, guys. We discussed about friction, but don't worry about it. Chapter 4, pressure, density, buoyancy, Pascal principle, density, right, mass density, Bernoulli's principle, temperature and heat, the units for temperature, linear expansion, specific heat, what is temperature, the laws of thermodynamics, latent heat. For waves and sound, I will probably focus more on open and closed pipes and the characteristic of a wave. And you guys just had an exam on this chapter. Be very careful with the math, guys. If I tell you that I have a charge, or if a charge has 1,000 electrons, that means that Q is equal to 1,000 times 1.6 times 10 to the negative 19 coulombs. The charge of the electron is that. Actually, negative, right? Other than that, I don't think there were problems with the math in these two chapters. In chapter 8 and chapter 7. Are there any questions for the exam, guys? I mean, it's open book, but...
Professor, how many questions are going to be?
I haven't made it yet, but I'm thinking there are 8.5 chapters, basically, right? Just one question about optics. I would probably say 2 questions about this, 2 about this, or 2, 4. I would say 3 about this, 7. 2 here, 9. 2 here, 11. 3 here, 14. 15, just 1 there. 17, 18. Say 20 questions. Expect 20 questions, guys. You have 3 hours almost. Is that okay? All right.
It's okay.
And
Huh?
no chapter, professor, is not on the SAM optics.
Yeah. So what we did today, just one question.
Okay.
Yeah, you guys are good. Okay. So I would probably say either reflection or refraction. One of those. You guys have access to all your quizzes, right? And the exams.
Yes.
So that will help you a lot. The web assignment. Oh, I have to put the grade for web assignment 8. There are problems that you guys can use to study as well, but the problems or the math in the exam will be simple. All right, won't be difficult. All right.
We start at 3:30.
Huh?
We start the exam at 3:30. Yes, the same time for the course.
I don't get it. What was your question?
No, I was asking if the time for the exam. Sorry, the time for the exam is 3:30.
3:30 till 6.
Okay, thank you.
The final exam is 20% of your grade. Just remember that. But as I said, you have the study guide there, and you have your quizzes, your tests, and I'm doing office hours on Monday. So if you guys have any questions, please let me know. It was a pleasure teaching you guys. I know we didn't get to meet in person, but who knows, maybe next semester or during the summer if you're still here. If not, best of luck, guys. Remember that course evaluation. Did you guys do the course evaluation or not yet?
I did.
Okay, thank you. We need that. Okay, we need the feedback. All right, guys. That's it. I will see you guys later then.
Thank you, Professor. Please don't forget to upload again the study guide, please.
Oh, yeah, no worries.